In this video, we're going to be looking at quantum theory and the discovery of new particles. So, in the early 20th century, many scientists thought there were just three fundamental particles, which is a particle that cannot be divided into smaller particles, or also known as an elementary particle. These three particles they thought were the electron, the proton, and the neutron. However, developments in quantum theory in the 1920s and 1930s suggested the possibility of other subatomic particles with some very peculiar properties. So what is it in quantum physics that made scientists believe that there are other fundamental particles? Well, first let's look at how we learned that energy and matter are interchangeable. So we have energy is interchangeable with matter. Now energy is made up of photons, which do not have a mass, and matter is made up of particles with mass. So this interchangeability between matter and energy leads to some very intriguing questions. How can matter with mass all of a sudden be converted to energy? So that must mean that there must be something there that cancels out this matter. That's where we're going to get to something called antimatter. Along came Paul-Adrien Maurice Dirac, who predicted the existence of peculiar particles known as positive electrons. It is Dirac's calculations that actually predicted that such a thing as antimatter could exist. So antimatter would be a particle that is the opposite of that of its corresponding particle. So same mass and everything, but it has an opposite charge, much like an electron and that positive electron that we learned of called a positron. So as a recap here, quantum theory predicts that each kind of ordinary particle has a corresponding antiparticle. If we were to think of a celebrity example of a particle and an antiparticle, it would be Homer Simpson and Albert Einstein. One of the startling properties, though, of antimatter is that collision between a particle and its antiparticle will annihilate, which means both particles create a pair of high-energy gamma-ray photons traveling in the opposite direction. So right here we have a positron that will combine with an electron to annihilate each other to create two gamma rays of zero mass. We have two things with masses that create pure energy. And that is what happens when we have an annihilation, or when a particle and its antiparticle combine. Let's take a look at some particles and their antiparticles. Here I have an electron and its antiparticle being an antielectron. Here I have a proton and its antiparticle being an antiproton. Here I have a neutron and its antiparticle being an antineutron. Now, if we look at the symbols of the antiparticles compared to their particles, for an electron and proton, these are the two where this occurs, all we need to do is change the charge. So here we have a P, which stands for proton, and I just put a negative. But for most particles, what we're going to do is just put our particle symbol and then just put a bar over top of the particle symbol to denote that it is its antiparticle. The discovery of a positron or an antielectron has really helped technologies evolve over the years. It is the discovery of the positron that made it possible to develop a powerful new medical diagnosing instrument. The positron emission tomography is an imaging technique that uses gamma rays from electron-positron annihilations to produce images of cross-sections through a patient's body. A computer can then generate a 3D-dimensional image by combining successive plane images. Now, scientists have been wanting to study these new and interesting particles that are theorized. So what they did is they came up with something called particle accelerators. Now, the thing is, we have to overcome this strong nuclear force that holds the nucleus of the atom together. So we have to put in enough energy, and in this case, which is kinetic energy, into these atoms that we're shooting around kind of like a racetrack and have them collide so that we can overcome the strong nuclear force, which is created by what we believe to be gluons, which is a zero mass mediating particle. Then we can split the nucleus of these atoms and see what is it that exactly makes up this nucleus. Is it just protons and neutrons? Well, then we started thinking, maybe we could even split protons and electrons and see what makes up protons and electrons, or see what makes up neutrons. So we started then making something called hadron colliders, as you'll find out that protons are essentially something called, and neutrons are something called hadrons. And we found out that these protons and neutrons are actually not fundamental particles, but they're made up of something called quarks. But we did find out that an electron is in fact a fundamental particle. So particle accelerators were originally developed for pure research, but now they have many medical and industrial uses as well. Many hospitals use accelerated particles for generating intense beams of X-rays that can destroy cancerous tumors. Bombarding elements with particles from cyclotrons produces radioactive isotopes for diagnostic techniques, radiation therapy, and testing structural materials, and numerous other applications. Particle accelerators can make a variety of specialized industrial materials by, for example, modifying polymers and implementing ions in semiconductors and ceramics. Accelerators are also a powerful tool for analyzing the structure and composition of materials. Particle accelerators have even been used to verify the authenticity of artworks. So as a recap in this video, we looked at particles and antiparticles. Now, when we shot these around in particle accelerators, we found out that we could separate our atoms of what we known before, electrons, neutrons, and protons, into two different categories called hadrons and leptons. Now, leptons turn out to be fundamental particles. So these have antiparticles. So the fundamental lepton, an example of one, is an electron. And its antiparticle would be the positron. So that's just an electron with a positive sign. Now hadrons, we found out, can be broken down even more. Hadrons could be broken down, and we found this out by using something called hadron colliders and the very famous Large Hadron Collider, into something called baryons and mesons. Now baryons are particles made up of 3 quarks, whereas mesons are particles made up of 2 quarks, a quark and an antiquark. We'll get into quarks in another video. But the one thing is, baryons are made up of 3 quarks, and these turn out to be protons and neutrons. Now, protons and neutrons are going to be our particles, whereas our antiparticles are going to be antiprotons and antineutrons. So now these baryons are held together by something called the strong force. And now my strong force consists of a particle without a mass called a gluon. Whereas now my leptons, they relate to something called a weak force. And now my weak force tends to happen in beta decay. And that's when we have a neutron becoming a proton through the release of an electron. And that has to deal with our weak force. So that there is a quick review of everything we have learned in this lesson.